Okay, in short, vertical asymptotes are where the denominator is equal to 0. And it's not a whole. So the first thing you always do is figure out whether you've got a whole first by factoring as much as you can and seeing if there's like factors top and bottom. If nothing cancels out, then anything left in the denominator, when that's set equal to 0, will become a vertical asymptote. Okay? And vertical's up and down. Yep. And the rule is vertical asymptotes will never, ever be able to be crossed. The function will never cross a vertical asymptote. It's not necessarily the case with horizontal, but verticals are hard and fast, a line in the sand, never will be crossed. Okay? And those, again, you just find by setting the denominator equal to 0 after you've factored out any potential holes. The horizontal asymptotes happen under 3 different scenarios. And it all has to do with the degree of the numerator and the degree of the denominator. Everybody understand what degree means? Okay, so reviewing degree. Degree is the largest exponent in the numerator and the largest exponent in the denominator. You always want to rewrite any polynomials in decreasing order where your leading coefficient and your leading term is the largest exponent. Okay? So you're going to be evaluating just the exponents of your leading term in the numerator and the denominator. The 3 cases are the leading term in the numerator is greater than the denominator, the leading term in the numerator is equal to the leading term in the denominator, and the leading term in the numerator is less than the degree in the denominator. Those are your 3 cases. Okay? And if you look at the sheet I handed out, number 1, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the line y equals 0, which is the x-axis. If the degree of the numerator equals the degree of the denominator, then you divide the leading coefficients and set that equal to y. Okay? And then if the degree of the numerator is more than the degree of the denominator, you divide using long division. And what's interesting is when you divide using long division, the remainder is the oblique asymptote. Not the quotient. Not what you get, but what's left over ends up being, let me see if that's right. Then the degree of the denominator, divide to find the asymptote, ignoring the remainder. When the difference in degree of 1, the asymptote will be oblique. Okay, so I was wrong. It's the quotient. It's the quotient. So, and it only works when the degrees are different by only 1. Okay, it's going to be an oblique asymptote if it's like an x cubed on top, x squared on bottom. Okay, so let's just do an example of how to find asymptotes. I can. So let's do one where the degree on, I'm going to do one out of each. Find my 3 scenarios here. All right. Okay, so let's first factor if we can. So on top it ends up being, if I do bottoms up, x minus 5, x plus 4, then I divide by 2. So on top I have 2x minus 5 and x plus 2. Follow me there? In the denominator then, x squared plus 10x plus 24, 6 and 4. Is that right? Divided by 3. So I have x plus 3, or 2, sorry, and 3x plus 4. Okay, I factored it. So what is glaringly obvious now? X plus 2, so where is my hole? The x value is negative 2. How do I find the y value of the hole? Plug it back in after I've canceled my terms. Okay, so technically this is gone. I still have a hole at negative 2. 2 times negative 2 minus 5 over 3 times negative 2 plus 4. Negative 4 minus 5 is negative 9. Negative 6 plus 4 is negative 2. So it's 9 halves. So my hole happens to be at negative 2, 9 halves. So that's my first thing. I found a hole. Okay. Using what we learned yesterday, now where is my intercept going to be? X-intercept. How do I find x-intercepts? Set the numerator equal to 0. So I've already canceled my terms out. So it's going to happen at 5 halves. That's it. I have one x-intercept and it happens at 5 halves. So this graph's going to go through the x-axis at 5 halves. Okay. Now, we're going to talk about horizontal and vertical asymptotes. Horizontal, look at what you started with. Don't look at the factored. Okay? I'm going to compare the degree on top to the degree on bottom with the original function. They're the same. So I know my horizontal asymptote happens at y equals 2/3. That line. Horizontal line at 2/3. You just divide the leading coefficients when the degrees are the same. Okay? My vertical asymptote happens where? Negative. Right? I'm going to figure out where this is equal to 0. Okay? So it is the line. So this is my horizontal. My vertical asymptote happens at x equals negative 4/3. My hole is at negative 2, 9 halves, I think is what it was. My x-intercept happens to be at 5 halves. 5 halves. 0. So I'm starting to pull the pieces together that are necessary to give me a picture of what this graph looks like. Okay, if I remember, what's 2.9?
Wait.
2.9, or whatever chapter we're in.
Oh, 6.9?
Yeah. Is it graphing?
It is oblique asymptotes.
Okay, so we won't talk about obliques today. Okay, so we'll just focus on horizontal and vertical today. Talk about obliques tomorrow, which is your last day, or you're gone today?
Gone
Tomorrow. Okay, we'll talk about obliques tomorrow, and then Thursday put it all together and actually graph from all of these. But for now, you're just trying to find each one of these items. So let's do another example where the degrees aren't the same. Yes.
If you take a free day, does it count for the, like...
I don't think so.
Okay, so it's still considered excused and it won't count towards your final thing?
Yeah. And as I'm writing this, I think it's going to be easier for me just to talk about obliques now. And then the only piece left is really finding your y-intercept. So we should be able to, with all the information we're doing now, use this sheet to graph. Because I think most of the web work problems that are left are actually identifying the graph or finding different things. There's no reason we can't pull all this together into one. So on top, I've got a degree bigger than the bottom. How can I figure out whether there's any holes here? I need to factor top and bottom. And in the top, I can factor an x out. The bottom, I can factor an x out, right?
Yeah.
So I really just have let's just put an x at the end. X cubed plus 2x squared plus x plus 2. Is this factorable like a quadratic, the numerator? Yeah, it is. And because if I pretended it was x squared minus 3x minus 4, it would be negative 4 positive 1, right? But we're going to make it x squared minus 4, x squared plus 1, and then I still have this x out there. Okay, this factors to x plus 2x minus 2. Okay, numerator's factored. Now, the trick one of the things that I use as a trick, instead of using all of the possible zeros and using synthetic division, I really care if the roots are the same, because that tells me holes. If they're not the same, I don't really care how it factors. Other than I need to solve the denominator. Okay, so I'm going to see if 2 works and negative 2 works first into this function in the denominator. I don't do that. I do 1, 2, 1, and 2. Nope. Let's try negative 2. 1, negative 2, 0, 0, 1, negative 2. Yep. X minus, or x plus 2 is a factor. And what's left? X squared, because it started as x cubed, x squared plus 1. So I have x still, x plus 2, and x squared plus 1. So I actually have one hole that's imaginary, right? Because when I solve x squared plus 1 equals 0, that's square root of negative 1, plus or minus I. Doesn't help me. That's just it's not gonna be anything on the graph. But the other hole happens to be at negative 2.
Wouldn't that cancel?
Yeah, it cancels.
Yeah.
And 0.
Yeah.
Sorry, and 0.
Yeah.
0 is a hole also, because the x's cancel. So I have a hole at 0, I have a hole at negative 2, and then the other hole is imaginary. Okay, so my first piece here is to identify if I cancel these 2 pieces, actually 3, all I have left is x minus 2. So interestingly enough, this whole mess is going to be a line, look like a line with two holes in it. Y equals x minus 2. Because everything else cancels. So when x is 0, y is negative 2. And when x is negative 2, y is negative 4. So my 2 holes happen at 0, negative 2, and negative 2, negative 4. Everybody see that? I just cancel everything that's common, and whatever's left is x minus 2. Okay. Now, when I look at vertical asymptotes, there won't be any because everything canceled. And now my degree on top is 1 more than the degree on bottom. Right? So I have to do long division to figure out what the oblique asymptote is. Okay, more than likely when I do long division, it seems to me it's going to be, well, let's just do it. X cubed, I'm going to do it with factoring the x's out. X cubed plus 2x squared plus x plus 2 goes into x to the fourth plus 0x cubed minus 3x squared plus 0x minus 4. Placeholders. Zero x cubed minus 3x squared plus 0x minus 4. So x cubed times what is x to the fourth? X plus 2x cubed plus x squared plus 2x. Change my signs. Negative 2x cubed, negative 4x squared, negative 2x minus 4. Now, x cubed times what? Minus 2. At this point, I can stop. You don't have to do the whole problem. Because I know when I multiply negative 2 by all this and then I subtract it, I'm going to end up with something that I can't divide into anymore. That's my oblique asymptote. X minus 2, which happens to be what looked like the graph of the function. So for fun, I'm going to graph this on Desmos. Let's see what it looks like. I'm going to find which problem it was. To the fifth minus 3x cubed. The line x minus 2. So it's just following its asymptote, which is really kind of strange, but you see the holes. Well, there's one right here, I think. Is that where we had it? 0, 2, 0? Maybe that's not a hole.
I don't know if it shows holes or not.
Yeah, it may not. Maybe that's just the intercept.
There was a hole at negative 2.
So right here is one hole, and then here was the other one.
Yeah.
So on this graph, if we were to graph it by hand, we'd just put an open circle right there and right there. Then we would dash in the line where the oblique asymptote is, which is actually the line. So to have such a complicated function that is actually linear when you graph it, it's kind of an interesting thing to think about. Okay. Let's do one more. This time we'll do one. Well, let's do another one. Do you guys need practice on long division or not? Okay, let's just do one that's the other way then, where the degree on bottom is less than the degree on top. Still have to factor the denominator, unfortunately, because I need to know where the vertical asymptotes are. So first thing I'm going to do is factor the numerator. I'm going to pull out a negative, because that leading term, when I work with it, should always be positive. So I can now do bottoms up. X squared minus 25x plus 24. X minus 24, x minus 25, divided by 3, or sorry, 1, not 25, divided by 3. So in the numerator, it's going to be x minus 8 times x minus 1/3, and it's a negative in front. And then the denominator, well, I'm going to try 8 to 1, negative 8, 1, negative 8. 1, 8, 0, 0, 1, 8. And there it is. So I know x minus 8 is a factor, and the other is x squared plus 1. So there's my hole. To find y, just plug it back in. My x-intercept is going to be at 1/3. Okay. And my vertical asymptote is not there. It's imaginary. So there's no vertical asymptote. There's no number I can put in for x that'll make that 0. Okay. Horizontal asymptote then, looking at these two. What is it? Yeah, y equals 0 is your horizontal. Okay. And the last thing really is to figure out what the y-intercept is when you're graphing these. Well, take 0 for every x value. What do you have left? Negative 8 over negative 8. The y-intercept is 1. We can piece all of these together on a graph now and physically graph with all of these asymptotes, holes, zeros, and kind of get a sketch of what it looks like. Okay, so today we'll just call that good. Tomorrow then we'll just spend time graphing. We'll practice a couple where we actually physically graph them, and then we will be done other than doing the same thing on Desmos or graphing calculator and identifying the different pieces from the graph. Okay.